In this segment, I want to talk about processor design and evolution, including covering how processors are actually made, the changes in technology that have occurred over the years, as well as changes in packaging and power consumption. Now, when most people think of a processor, they think of a chip like this, for example, this Intel Core i-series processor that I have here. Now, when most people look at this, they say, oh yeah, that's a chip, but what they're really looking at is the package. What I'm really interested in, what we're going to talk about more here, is what's inside the package. Now, in this cutaway view, I have a magnified image of one of Intel's latest Core series processors, and underneath this metal cap, you can see the actual processor die. The die is the actual circuit that comprises the processor. Now, this circuit is incredibly complicated. These circuits can have upwards of 1 billion or more transistors in them. So it's an incredibly complicated circuit. In fact, I would have to say the processor is one of the most complicated components that is manufactured by man today. So let's look at how these things are actually made. Well, processors, the raw material that go into processors is silicon. And I have an example of a chunk of pure silicon right here. Now, silicon is the second most abundant element on the planet. The only thing that we have more of is oxygen. One thing, though, silicon is rarely found in any kind of a pure form. It's mostly mixed with oxygen in the form of silicon dioxide, which most of us know as quartz or sand. So, in fact, sand is mostly silicon. So, many times you've probably heard that, electronic circuits are made out of sand, and that's largely true. So what happens is we take the sand, melt it down, and put it through a purification process until we extract the 99.999% pure silicon. Now, even that's still not ready to make chips out of. We need the silicon not only to be pure, but to be in the form of a crystal. So what happens then is the silicon, the pure silicon, is melted in a vat, and a seed crystal, like the one I have here, is dunked into the vat of molten material. It's slowly turned and then pulled out. Now, if you imagine this vat of molten material, it's kind of like melted glass. It's sort of thick and taffy-like. And as the crystal begins to pull out, some of the material sticks to it and begins to harden. So what happens is this seed crystal pulls out of the vat, and you can see a bunch of material sticking to it. And they pull at first rapidly until we have a very thin stem forming, and then finally more slowly until a wider and wider crystal begins to emerge from the vat. This is an example of a pure silicon crystal that I have here that was grown in one of these vats. As you can see, the shoulder of the crystal gets wider and wider as it is pulled out. This is like millimeters per hour. It's a very slow process. Now, once the crystal reaches the diameter that is intended to be, then the process speeds up a little bit. It's pulled out a little bit more quickly until basically what we have is like a cylinder. Imagine a cylinder of this crystal material being pulled out of this vat. Once the cylinder has reached its final length, which is usually a couple of feet long, then the pulling process goes more quickly and we end up with a tail. They want to actually have a sort of a gradual pull out of the material from the vat to prevent any kind of thermal shock. Now, the tail on this crystal is very short. It's very short here, as you can see. In fact, this was an aborted crystal process. Normally, the main body would be not just an inch here, but would be several feet tall. This, in fact, is here as an example of a tail of a more complete crystal. So if you can imagine, this thing was several feet tall, and then this was the tail that's basically cut off and is considered waste. The head and the tail are then chopped off of this crystal. So now what we have is this cylindrical crystal of silicon. Head and tail are cut off. This is then put into, it's ground so that it's perfectly round, and then it is put into a saw that cuts it into thousands of plates called wafers. I have an example here of a wafer that was cut from one of these crystals. You can see that it's round and it's very thin. It's less than a millimeter thick. Thousands of these usually come out of one single crystal. Now, the wafer would then be polished to an absolutely flat surface, better than most mirrors, a mirror polish. And then what we have is called a wafer, and this is the sort of the raw base building material for making chips. Now, what happens is the wafer is put into a process that's a photolithographic process. We take a mask, which is, could call it like a negative. We shine a light through it, and we literally etch the various dye into the wafer. I'm going to show you an example here. This is an example of a wafer that has 177 finished die etched into it. As you can see, they're just one after the other, rows and rows and rows of them. One mask was used to produce this, or I should say one collection of masks, because each of these die is not just one image that's put on this wafer. It's a stacked series of images, usually 20 or more layers. And through the photolithographic process, material is coated onto the wafer, then it is etched with the ultraviolet laser, then portions are washed off, and we literally have like a cake building process, a layer upon layer upon layer, until this very complicated series of circuits is assembled. Then, once the wafer is complete, the individual die are then cut out of it. So then we end up with individual square processor die. Now, a typical die, might be something on the order of these sizes here. I have I made up some pieces of paper that are about the size of most modern processor die. They can be anywhere from usually 10 millimeters to 20 millimeters square on each side. Some are more rectangular, some are square. Okay, so now we've seen the basic, building process of making processors, but let's take a look at how this technology has changed over the years. Processors have been made for nearly 40 years now. The first one came out in 1971. What was different, from then to now? Well, a couple of things that have changed. One is the size of the wafers. This is an example wafer from around 1973-74 when they were 3 inches in diameter. As you can actually see, this one has a series of chips imprinted on it. This one was never cut. The chips were never cut out into the separate die. Now, wafer sizes have increased over the years. Most recently, we had a transition from 8-inch wafers to 12-inch wafers. And what that means is that the wafers that are being used for most chips today are 12 inches in diameter. Now, as the wafer size increases, the number of chips that can be imprinted on them go up. For example, this wafer image that I have here was actually originally an 8-inch wafer. And with the 8-inch design, 177 separate chips could be etched or fit onto this wafer. Well, when this was increased to 12 inches, they began making the same chips on a 12-inch wafer. They were able to make 449 chips on the same exact wafer. So in the same amount of time, they are now making, nearly or more than twice as many chips. As the wafer size went from 8 inches to 12 inches, the surface area grew grew 2¼ times. So we can have literally more than double the number of chips being produced. So these are some of the technology changes that have happened. The wafers have gotten bigger. One other thing has been going on, though. The componentry that goes into each of these die has become smaller and smaller. When processors were first being made, the very first processor in 1971 had components spaced 10,000 nanometers apart. That's 10,000 billionths of a meter. Today, we are making chips with the componentry spaced only 32 nanometers apart. That's hundreds of times more dense, more components fitting into the same space. So while the die of a processor has remained relatively the same since about when the 486 came out in 1989 to the present, the actual individual size of the processor chip within the chip has remained the same. But the number of components has gone up tremendously. The 486 had 1 million transistors on it. Today we have processors approaching 1 billion transistors. So, as you can see, the two big changes that have occurred in processor manufacturing is going to larger and larger silicon wafers on which we etch the chips. And then each die, while the die has remained relatively the same size over the years, more and more components are being crammed into them. Now, let's take a look at sort of a timeline of processors over the years, PC processors especially, and look at how not only the processors have changed, but the packaging and even cooling issues as well. I have assembled here nearly 40 years worth of processor history, I thought we could take a look at this. Now, in 1971, the very first processor that was introduced by Intel was called the 4004, and I have an example of that right here. Now, this is not an actual 4004 chip, but it looks like one. Real 4004s are actually quite rare and considered to be collector's items today. But this chip is exactly the same size, shape, number of pins, and everything as the original. Now, on it, I have a little white square. That represents the actual die size of the original 4004, the first processor. As you can see, it's pretty tiny by today's standards. Now, next to it here, I have an Intel 8088 processor. Now, this processor was introduced in 1979 and is the first PC processor. The IBM PC came out in 1981, and this processor actually came out of an original IBM PC motherboard. The original 4004 ran at up to 3/4 of a megahertz. That's 3/4 of a million cycles per second. The original PC ran at just under 5 megahertz. Technically, it was 4.77 million cycles per second. Now, after the first PC came out, the next processor to be released was the 286 processor. Now, the 286 came out in 1982. I have 3 different examples of 286 processors here. They are noted by, they're just a different physical configuration. This first one, this uses pins that plug into a socket. This is a different design which uses pins around the edge of the chip. And then this one was one where that had no pins. The pins were actually in the socket on the motherboard, and there were just lands around the chip. Now, what's interesting is that just in the last few years, this type of packaging has returned, and most of Intel's processors now use this land grid array, they call it. So at this point, processing speeds went up to about 10 to 20 megahertz. Now, here we have a 386 processor. The 386 came out in 1985. And this had about 300,000 or so transistors on it. So the transistor count had been going up. We had started out around 2,000 in the first processor. We went to 30,000 in the first PC processor. We have about 130,000 in the 286, and now nearly 300,000 approximately in the 386 processor. Now, the 386 is also known as being the first 32-bit processor. What's interesting is that even though that chip came out in 1985, we didn't really have 32-bit operating systems until a decade later, when Windows 95 came out. So sometimes the processor technology is ahead of the software that actually supports it. Next, we have an Intel 486 processor. The 486 came out in 1989, and this was the first processor to have over 1 million transistors on it. It was about 1.2 million transistors, actually. This also was the first processor that began this, several changes happened in that processor. One, it was the first processor that had built-in cache memory. And that was sort of a revolutionary breakthrough because processing speeds had been exceeding the speed of memory, memory chips, at least affordable ones. So by building memory into the processor, it sort of brought along its own little high-speed portable cache buffer of memory, which made things work incredibly faster. So the 486 was a breakthrough. Then we have here the 586 processor, which really wasn't called a 586, it was called a Pentium. The first Pentium came out in 1993 and had just over 3 million transistors on it. The Pentium was also, like the 386 and 486 before it, was a 32-bit processor. Now, that concept of cache I was telling you about, yes, the Pentium also had the cache built into it, but this was what we call level 1 cache. During those times, level 2 cache was still found on the motherboard, and therefore it ran at slower motherboard level speeds instead of higher or faster processor level speeds. So the next processor would change this radically. This was called the Pentium Pro, which is right here, which came out in 1995. Now, the Pentium Pro was really a revolutionary chip. For one thing, it's huge. It's physically probably the largest single chip I've ever seen. And the reason is because there's actually not one chip in there. There's 2. This, in fact, represents the actual die of the Pentium Pro processor, and if I set it on here, you'll see why this chip was rectangular, because there were basically 2 chips side by side. One of them is the actual processor chip, and it has its own built-in level 1 cache memory. The other chip next to it is a level 2 cache memory chip. Now prior to this, the level 2 cache had been on the motherboard. Now it was part of the processor, but it was still a separate chip. Now this dual chip in a package processor was very expensive to produce, so it wasn't very popular because it was expensive. So Intel was working on the problem of how can they make this type of a chip with the cache built into it less expensive. Well, what they came up with was the concept of a circuit board as a processor. Now this is actually a Pentium 3 processor, but the Pentium 2 and 3 both did this. In fact, these are really P6 or 686 processors, just like the Pentium Pro. And what we have is the actual processor chip here and then cache memory alongside of it. And what this allowed Intel to do was to literally buy cache memory chips from third-party suppliers, like the ones on this are actually from Samsung, and integrate them into a circuit board. Now this type of a board would plug into a slot. Now I think Intel was possibly a little vain about this. They didn't want you to see that they were using other companies' cache memory chips on here. So what they did in the Pentium 2 packaging was they built it into a plastic case. So this little circuit board is in this thick plastic case, has a heat sink built onto it, and in fact they even have a picture of the die of the processor on the side. This was the first processor that I knew of that featured what I would call decoration. The Pentium 3 was really the same thing. The Pentium 3 was just an enhanced version of the Pentium 2 processor. Now the Pentium 2 came out in 1997 and the Pentium 3 came out in 1999. All of these continued that technology of building the level 2 cache into the chip, but it was separate chips. It was a multi-chip package. Well, finally, both Intel and AMD created small enough transistors. The process had gotten tight enough to where they could pack the level 2 cache chips into the main processor just like the level 1. Now in continuing this evolution, talking about processor packaging, most of the time when a processor is made, you don't actually see the die. It's covered up. Well, some chips were made where you did see the die. I showed you this Pentium 3 and you can actually see the raw silicon die on top of this chip. That's the actual silicon base of the processor. Now it is flipped upside down, so the circuits themselves are not visible. They're turned around. But still, that's the raw silicon die. Now there was a problem with this design that when you attached a heatsink to it, it's basically perched on this little pedestal of silicon, and if you put pressure on it a little bit too much to one side or the other, you could crack it. Silicon is like glass. In fact, here I have a piece of a wafer that I broke earlier, and it shatters like glass. The shards flying everywhere. The edges are extremely sharp. It's very brittle. So what would happen was when you would put a heatsink on a chip like that, and here's an example from AMD. This is a AMD Athlon processor with the raw processor die sitting right in the middle of the chip there. If you put pressure on it, it would crack the die. What AMD did was put rubber pads around each of the four corners to try to mitigate that problem, but still it was happening all too frequently. So in more recent designs, both Intel and AMD have put covers over the processor die. This is an example of a Pentium 3 that has a couple of changes. Number one, the level 2 cache, which used to be separate chips. These are both Pentium 3s here. The level 2 cache is now built into the processor die, and then the die is now covered with a metal heat spreader. And they call this a heat spreader because it helps spread out the heat. It gives more surface area for the heatsink to attach to and dissipate the heat from the processor. Also protects the die, the raw silicon die, from any kind of damage. So these are much more durable. Okay, now we'll move on. The Pentium 4 processor, which I have an example of right here. Right here. This is a Pentium 4 processor. That came out in the year 2000. Also in 2000, we had the first processors that hit 1 gigahertz in operation. That was kind of an important level of speed. From 0 gigahertz to 1 gigahertz, it took 28 years. What's interesting is it only took something like 18 months to go from 1 gigahertz to 2 gigahertz. But so this was the Pentium 4 processor. Now, in 2003, AMD came out with a revolutionary new chip design. This was called the Athlon 64. This was the first 64-bit chip. Remember I said earlier how the 386 was the first 32-bit chip? Well, all of the chips from the 386 up through the Pentium 4 were mostly 32-bit designs. AMD, in this case, took the lead from Intel and created the first 64-bit design. And it was Intel who ended up copying this design and integrating it into the Pentium 4 and some of their other new Core series processors. So we now have 64-bit processing technology where the chip can operate on 64 bits of data at a time. So this was the Athlon 64, came out in 2003. Now it's interesting that it wasn't really until 2009 when Windows 7 was released that we had what I consider to be a mainstream 64-bit operating system. Yeah, there were 64-bit versions of Vista and Windows XP, but they were not what I would consider completely mainstream. Windows 7, on the other hand, is really the software jump to 64-bit. I think we're going to see most systems running in 64-bit mode with Windows 7. Okay, now, continuing on, this is an interesting chip here. This is a Pentium D processor, which was the first dual-core chip. See, up until this time, processing speeds had increased and increased from, under 1 megahertz up to over 3 gigahertz. In fact, 3.8, nearly 4 gigahertz. But what was found was that we couldn't keep increasing speeds because heat production was going up tremendously. So rather than increase the raw speed of one chip, they came up with the idea of putting multiple chips in the single processor package and basically have multiprocessing. So we could run, we're running multiple programs at one time, and now we have multiple chips to run these programs. So we effectively have a faster system. First we had dual core, now we have quad core chips. This last processor I have here is one of the Intel's latest Core I series, and this is a quad core chip. There are 4 chips in here. Now the first dual core chips were actually 2 single cores mounted side by side under the little heat spreader there, and just likewise the first quad core chips were 2 dual core chips mounted side by side. But as the processor manufacturing had evolved, they now make both dual core and quad core chips all on the same die. So as we've seen, the processors have evolved tremendously over the years in their physical packaging. We had what started out as very small chips. We went to larger chips. We went to even cartridges, if you want to call them that, because of the extra cache. But now the concept is to bring everything back onto the single die, and now even putting multiple cores. Now I thought we'd take another look at the cooling of these processors. Over here I have an example of the evolution of processor cooling over the years. Now, when the first PCs came out in the early 80s, they didn't even have heat sinks on the processor. Today, you wouldn't think of having a processor without some type of a cooling device mounted on it, but up until, in fact, the 286 and even early 386 systems, there were no heat sinks used on processors. The processor could just ran cool enough and only used a few watts that it wasn't a problem. But when we started getting past 33 megahertz, when we went to like 66 megahertz, 100 megahertz and faster, we started to require cooling. This was what was used on some of the early processors that required a heat sink, and as you can see, it's just a passive metal radiator. No fan or anything. There was enough airflow in the system to cool it. When we got to 200 megahertz, we needed bigger passive heat sinks. This was for about a 233 megahertz processor. But when we went past 233, we found that the airflow in the system wasn't sufficient. You either need a really large, metal heat sink, or you could use a smaller one and put a fan on it. So what happened was, instead of having something big like this, we had something smaller, but it had a fan on it. So this was around a 200 to 300 megahertz processor cooler. As we went up to 400 and 500 megahertz, the processing coolers got bigger, the fans got bigger. Over here, we're up to 1 gigahertz, 2 gigahertz, and then 3 gigahertz and beyond. As you can see now, what has started out as just a small passive little heat, cooling device is now a massive finned assembly with a large fan. Now you can tell that sometimes on many of the newer heat sinks, they also use a copper core. Copper is one of the best conductors of heat, much better than aluminum and many other metals. In fact, so a lot of processors are now, or heat sinks, I should say, are made using copper as part of the core. So as you can see, we've had a lot of changes occurring in processors over the years. They've gone from very small chips to, very large chips, cartridges. Now we have multi-core technology. The heat sinks to cool these devices have grown in size and complexity over the years. And all of this has taken place in the last 40 years since the processor first came out. All right, in this segment, I want to prepare the case for the build. Now, this is pretty much the case I purchased. It's the Enermax Vostok. It's just as I received it, and it's really not ready for me to use. I need to make some changes to the case and maybe do some upgrades in order to get this ready for the system that I'm going to build. Number one, I'm going to take out these quick install no-tool drive mount brackets because I'm going to use actual screws to mount the drives. I don't like these. They don't hold the drive securely enough for me. Now the case does come with an assortment of screws, which is nice. Most cases do. If they don't, you'll need to procure some screws. You can buy usually kits from different suppliers. This case also came with a fan and some other components, but we'll get to that. Now, in order to continue getting the case ready, I'm going to take out the power supply and remove the front panel. Now, in order to do that, I'm going to lay the case down on its side. Now, even if I wasn't going to replace this power supply, I'd be removing it just so I could get easier access when installing the motherboard. But in this case, I am going to replace the power supply because it's not adequate. It's not adequate for the system I'm going to build. It doesn't have enough connectors, doesn't have enough power output, so I'm going to take the power supply out. It's secured by 4 screws on the back. I'm going to simply remove them and take the power supply out of the system. Okay, now that the screws are taken out, I can remove the power supply and put it to the side for now. Okay. Now, I'm going to take the front panel off so I can gain clearance for installing things like a front fan, disk drives, and other things. In most chassis, to remove the front panel, you simply push from the bottom, push outwards. Sometimes you might want to look to make sure there are no clips that you have to release on the inside. This one you just push from the bottom, and the front panel comes off. Now I have to snake out these cables. And now we have the front panel off. So I'm going to set that off to the side here. Okay, and then finally, I'm going to remove the other side panel. Most chassis you can remove, one side panel in order to install the motherboard. But if you can remove the other side panel, you get much more access for putting screws into the drives and things like that. So I'm going to take that panel off here. Okay, now we have a case really ready for me to begin assembling. It's as bare as possible. I've got the easiest access to everything. Now, a couple of other points to make. I said I was going to use a different power supply, so that's something you need to consider in advance. If you're going to use a different power supply, make sure you have it. I'm also going to use a different fan. Traditionally, the fans that just come with a case, even though this is a 120 millimeter fan, which is nice, it's a little bit noisier than I would like. It's also not necessarily a dual ball bearing fan or a hydrostatic bearing fan. So what I recommend is purchasing higher quality fans in order to install in the case when you assemble it. So at this point, we're ready to continue the build process by installing the motherboard and other components. Okay, now I'm ready to install the disk drives and the cooling fans. Now, I had mentioned previously that because I'm going to be installing 4 drives in a RAID 1.0 array, with 4 drives in close proximity at the front of the case, you can get a little bit of heat there. So I'm going to add a cooling fan to the front of the case. I'll also install the cooling fan into the bracket in the back of the case. Now, let's do the front fan first. In order to do that, I'm going to take a 92 millimeter fan that I had purchased separately, and I need to make sure that I've got the airflow